Okay, so today we're going to look at networks and their surrounding context. And so where a network is situated is actually equally important as the structure of the network itself. So there are certain things that you can do in certain contexts, for example, things that you can do in the privacy of your home, or maybe not things that you can get away with in public. And, it also plays a role in language. There are certain things that you can say in certain contexts, but if you say them in other contexts, it may start a fight or create gasps, even the same words. George Carlin has a lot of examples, and I'll refer you to George Carlin instead of repeating his jokes here. So it also has a major effect on the interactions within a social network, basically how we form the social networks and how the social networks evolve over time. And so far what we've examined are social networks without their context. And so the surrounding contexts are factors that exist outside the nodes and the edges of the network, which nonetheless affect how the network structure evolves. So an important idea here is homophily or homophily. And it's the idea we tend to be pretty similar to our friends as an aggregate. And the idea goes back to Plato. Similarity begets friendship. Provides an example of the ways different friendships can form introduction from a common friend. We can meet within the context of a group or a class that we're all taking. What you see here is the friendship network of middle and high school students. And the color of the circles is the race of the students, and the friendships tend to be based on race and based on which school they attend. So the social context here supports the triadic closure. It's a little hard to see from that diagram, but it's actually triadic closure is actually supported there. And the clumps are the context in which the people become friends. So is there a way to measure homophily? Given a particular characteristic of interest, is there a simple test that we can apply to estimate whether it exhibits homophily according to this characteristic? So let's assume we have a network with P is the fraction of male students and Q is the fraction of female students. So this is a friendship network for a small hypothetical classroom. The 3 shaded nodes are girls or female, and the 6 unshaded nodes are boys or male. If there weren't any cross-gender edges at all, then the question of homophily would be easy to resolve. It'd be present in pretty extreme tense here. So assume a network with the P is the fraction of male students and Q is the fraction of female students. If we independently assign each node the gender male with probability P and the gender female with probability Q, both ends of the edge will be male with probability of P squared. P is the probability that a particular student is male, and both ends will be female with probability Q squared, and you'll get a cross edge with probability 2 times P times Q. So if the fraction of cross-gender edges is significantly less than that 2PQ, then there's evidence of homophily within the network. In the picture here, 5 of the 18 edges are cross-gender friendships. Because P is equal to 2/3 of these students are male, that is, they're 6 out of 9, and 1/3 are female. So 2PQ is 4/9. So we'd expect 8 out of 18 to be cross-gender. So we actually have some homophily here. People are tending to form friendships with like people. We can get more sophisticated, and there's things that we can do like measure for statistical significance. And we can do that even if more factor levels are involved than just 2-level factor. So, what are some of the mechanisms underlying homophily? Well, there are 2 primary ones. One is selection. That's the tendency of people to form friendships with others who are like them. And social influence, the influence from friends to take part in certain activities, that peer pressure, peer pressure, peer pressure. And there are 2 types of characteristics that people have. There's mutable and immutable. And immutable are the attributes that are determined at birth. Mutable are the ones that can be modified. So, we can modify our behaviors, bring them in line with our friends via social influence, or, because we want to. So selection and social influence actually interplay with one another, and sometimes it's hard to separate them out. This can be done through longitudinal time-based studies. And with teen studies have suggested selection is far more of a factor than social influence by more than a small bit. And, of course, they talk about, the decision, as to whether to use drugs or take up smoking or whatever. Of course, there are other reasons why anti-drug programs don't work. This is Bud Out from South Park. The school hosts an assembly with an anti-smoking group, and of course, it causes all the kids to go out to the loading dock and take up smoking because the assembly was so uncool. Watch it for yourself. Good episode. So, they've done some studies about this, whether it's selection or social influence. And one study looked at 12,000 people and tracked obesity status and social network structure over a 32-year period. So that's quite a long study. And people tended to be more similar in obesity status to their network neighbors than an inversion of the same network where obesity status was assigned randomly. So what are the reasons that you might get people with like body types hanging out with one another? Selection effects in which people are choosing to form friendships with others of similar obesity status. Could it be because of the confounding effects of homophily according to other characteristics in which the network structure indicates existing patterns of similarity in dimensions that correlate with obesity status, or because changes in the obesity status of the person's friends was an existing, presumably behavioral influence that affected his or her obesity status. And basically, which ones of these ended up being true? Well, statistical analysis in this paper from Christakis and Fowler argues that even accounting for effects of type 1 and 2, there's significant evidence for type 3 as well. Obesity is a health condition displaying the form of social influences, with change in your friend's obesity status in turn having a subsequent effect on you. This suggests the intriguing prospect that obesity and perhaps other health conditions with a strong behavioral aspect may exhibit some amount of contagion in a social sense. We need careful analysis to determine if something is selection or if it's social influence, and may want to grab some McDonald's after this slide. Another factor that we can have in networks is affiliation. What are the organizations or activities that you're affiliated with? And, so far we've only viewed contexts that's outside the network, but we can actually move it inside the network. And we can look at activities which we'll call foci, or the focal points of social interaction. These could be your workplace, volunteer organizations that you're a part of, places where you hang out, boards that you serve on, etc., or websites to which you belong, or gaming groups that you take part in. That can be any type of affiliation really. So this is a Bi-Apartheid graph, which means you can separate it out left and right. That shows the individuals are affiliated with which groups or activities. So that's an affiliation network. People go on left, and the foci go on the right. So Anna participates in the Literacy Volunteers Organization and the Karate Club. Daniel only participates in the Karate Club. And these are useful for understanding patterns of participation, for example, board of director membership. So this leads to an idea of coevolution for social and affiliation networks. And this reflects that interplay between selection and social influence. If two people participate in a shared focus, we're both members of the Karate Club, that presents us with an opportunity to become friends. If two people are friends and I'm a member of the Karate Club, that may influence you to also join the Karate Club. And so we can extend our idea of closure as well. And we can also extend how we're connecting things. So we can connect two people in a friendship. We can connect a person to a focus. And so we get these different types of closure. Triadic closure, which is all people that you see in the top. Alice, Bob, and Claire. Alice knows Bob, Alice knows Claire. Alice introduces Bob to Claire. You get the triadic closure, assuming strong links. Focal closure, which is depicted in figure B, two people form a link where there's a focus in common. So Bob gets introduced to Claire through karate. And then membership closure, a person gains a new focus as a result of a friendship between two people. So person A and person B, Alice and Bob. Alice is part of the karate club and introduces Bob to the karate club. So how can we measure this triadic closure? In the past, it's been difficult to measure link formation quantitatively, but large online data sets have made some preliminary work in this area possible. For triadic closure, researchers have looked at how much more likely it is for a link to form between two people if they already have a friend in common, and how much more likely it is for an edge to form between two people if they have multiple friends in common. And this one was taken from email study that was done at a university. And you can see as there are a number of common friends, the likelihood of a link formation goes up. The black line there is the actual, and the red lines are mathematical models of what they expected the formation of friendship links or triadic closure to actually be based upon probabilistic models. Focal closure was probability that two people form a link as a function of the number of foci they are affiliated with. And to understand how this happens, they supplemented their email data with class schedules as a focus. And here, we can see the red is the mathematical model, but the black, the actual data doesn't line up with it. It does for, about 2 to 3 classes, but after 3 classes, one would assume, hey, if you're not, talking to that person after you've taken 3 classes with them, you're probably not likely to email them, even if you're taking 4 or 5 classes with them. And then last but not least is membership closure. What's the probability that the person becomes involved with a particular focus as a function of the number of friends who are already involved in it. This data shows the probability of joining a live journal community as a function of the number of friends who are already members. But there was actually also a study based on people editing Wikipedia articles and who they were likely to be in communication with. So, if I was in communication with someone who was editing an article on, Jakarta, is it likely that I'm going to end up having Jakarta as a focus of editing? That one actually turns out to be true as well. So, breaking up again the selection and social influences factors is quite difficult. In the Wikipedia case, they showed, selection, there was a rapid increase in similarity before the first contact was made, and then the social influence continued a slower increase in similarity between the editors. And so they actually had a measure of similarity between the 2 Wikipedia editors based on the number of articles edited by both divided by the number of articles edited by at least one. And so as they grew in similarity, they would eventually make contact and then continue to grow in similarity. And last but not least is the Schelling model. And you'll recall that homophily means we tend to be similar to our friends as an aggregate. This picture here is the only cafe on Danforth Avenue in Toronto, which is a place where I had the pleasure of living on the Danforth. And Danforth was really cool because you could go up and down the Danforth, and they had all these really nifty neighborhoods, ranging from Little Italy and Little Ethiopia on the east end to kind of Greek town on the west end, just before Danforth turns into the Bloor line. And then if you went south on Broadview, you could get to East Chinatown. So there were all these cool neighborhoods, and you could get all this delicious food and have all these different experiences just on one road in Toronto. We also see homophily in red states and blue states. Another example would be the combat zone in Taipei, which is where all the expatriates gathered in Taipei. So it has a different characteristic than the rest of the city. Or Kemang in Jakarta is another example. And I'm sure that you can think of some negative examples of this. That have taken place in United States history in terms of people segregating themselves or being segregated in different neighborhoods. So Schelling's model looks at the forces that lead to segregation in neighborhoods, and they're remarkably robust. So the model has two different types of agents. They're either agent X or agent O. And they can't change their characteristics. These are innate, once, if we're looking red state, blue state, once you're a Republican, you're a Republican. Once you're a Democrat, you're a Democrat. You can't switch those. Those are the immutable characteristics. Of course, I think political party can be mutable in some cases, but these are characteristics that people can't change. These are innate. So the agents stay type X or type O. The agents reside in cells on a grid, and the cell's neighbors are the ones that touch it. So each one can have up to 8 different neighbors because it's a grid. And each agent wants to have at least some of the other agents. It doesn't have to be all of its own type as neighbors. So there's a threshold T. And if fewer than T neighbors of the same type, then the agent will attempt to move. So, we can set T equal to 2 or 3. If I don't have 2 neighbors who are, in the same political party as me, then, I may attempt to move. Or if I don't have 2 neighbors that, have the same interests as me, I may attempt to move. So we set up our initial configuration. This is, an 2-dimensional array. Here we have the different agents, X1 through X11 and O1 through O11. And we basically measure their neighbors and see whether or not they have 3 neighbors that are like them. We mark a star with the ones that want to move, and the empty squares are, of course, places that they can move to. Lots of vacant space here. We move the agents. Now, there are different ways that you can move the agents. You can do it by row. You can do it randomly, but we want to move the agents to an area where they'll be satisfied with their new neighbors. And moves can cause previously settled agents to become unsatisfied. And if that's the case, then we find the ones who are recently unsatisfied and move them. And we keep doing that until everybody is satisfied. So the Schelling model ends up producing these large homogeneous regions, and spatial segregation takes place even though no agent is individually seeking or intending it to happen. We just want some neighbors who are like us. But basically, agents will attach themselves to clusters of others like themselves, and these clusters will grow as other agents follow suit. And so what you get is an unraveling of integrated regions. So here's what the Schelling model looks like in one run after only 20 steps, and after 800 steps, it's almost completely different, with the only integrated areas very close to around the edges. And, one would assume if you kept running that, you'd almost get complete separation of red and blue. So the implications of this are kind of quite depressing and stark. The underpinnings of segregation are already present in a system where individuals simply want to avoid being in too extreme a minority in their own local area. The Schelling model is an example of how characteristics that are fixed and unchanging, such as race or ethnicity, can be highly correlated with other characteristics that are actually mutable. So the mutable characteristics, the decision where to live, I can change that over time. To conform with similarities in other agents and mutable types, and that produces segregation. And as homophily draws people closer together along these immutable characteristics, you get a natural tendency for mutable characteristics to change, to move closer to our neighbors. And if this one's too depressing of a model, there are actually some kind of cool models that look at why people end up all giving standing ovations at concerts. based on the behavior of their neighbors that are similar in structure. So kind of interesting model that Schelling developed, and the mathematics aren't completely understood, even though it's a very simple model that you might be able to program with 150 or 151 experience. So we'll be doing a little bit of work with Schelling's model in the class. So go back and definitely take a look at that in chapter 4.